In this part, we are going to focus on astronomical images of the first kind, limiting to images taken without a tracker, using a wide field of view with lenses no greater than 24 millimeter, with up to 30 seconds exposure time using the DSLR type camera. These will primarily be images of the Milky Way galaxy with and without a terrestrial foreground. Milky Way is a relatively simple target, provided you have very dark skies. And you can see the Milky Way with the unaided eye. These are optimum conditions. Now, jumping ahead a little bit, we're going to have to buy a tracker. This image was shot at 140 millimeter camera lens. It was several images, probably 60 of them, shot at 30 seconds each and stacked in DSS. Again, no telescope needed, but a tracker equatorial mount is needed. After you purchase this equatorial mount, you're going to be able to take stunning images with your camera lenses, with your DSLR camera lens, like this, of the Horsehead Nebula, which is comprised of about, I think on this one, 60 exposures stacked at 2 minutes each. I'm really happy with the results. This is my first attempt to get 3 targets in one frame. M31, M33, and the star in the center is Mirach. And this is the upper right-hand corner is the galaxy Andromeda, and the lower left is the galaxy Triangulum. You'll notice that in this NASA image that there's a lot more cosmic dust. Now, this is sort of brand new for us as the backyard astronomers, getting such detail. And it's causing a lot of heated debate. A lot of photographers are saying it's just noise, nothing to see or hear, step along. It's in interstellar space and it's not in the localized solar system. I have different, as we shall see in ensuing imagery. If my theory is correct, some of this cosmic noise and dust will be present only in solar system images, and some of it will exist in deep space. We will monitor changes, such as weather changes. Now, I expect to find a lot of change in the solar system, and little to none in interstellar space or deep space targets. We shall see. I realize this study is a little out of the scope of this presentation, but we should be able to discriminate between solar system noise and deep space noise through narrowband imaging, where effectively we're going to take out the solar system influences of cosmic dust, and then we're going to focus in on the atmospheric, the cosmic atmospheric disturbances through narrowband imaging, of course. Well, let me make it clear, it's very doubtful that any kind of cosmic atmosphere, such as nebula, will be visible, changes will be visible. Well, it's very, very unlikely. There's too much distance, and time itself is an issue. Unless we caught something very dramatic, like a pulsar or something happening in that time of our prescient time, then we would visualize the change. There are other subtle ways where we might be able to differentiate a change in cosmic nebulas, and also the stardust or planetary dust that is still settling from some great cataclysm in recent times in our own solar system. It's a long, hard road down that road, but I have some ideas. Okay, after you have chosen your DSLR camera that you're going to use, we're next going to choose a lens, and we really need the tracker. Now we're going to start with Milky Way at 18 millimeter, 10 millimeter, 14 millimeter. We won't need a tracker for 30-second exposures, and we can expect stunning results provided you have chosen an area that has very dark skies. You can also image the Milky Way long before, shortly after sunset. It's a little difficult, but sometimes it's pretty good. This is one of the reasons why it's very difficult for me to get any video work done here. Well, any work for that matter. I got great opposition and adversity here. Another nice opportunity is you can get an adapter for the ZWO cameras, which are do not have an infrared blocker in them. You can get them in mono or color, and you can get an adapter to fit any of your Nikon or Canon lenses. This is the heart of your system, even down to stunning stackable Milky Way images. This is programmed to let you correct through imaging to where you always end up with a focused landscape, even though you're tracking the stars for a long period of time. It has several adjustments, 12 times, 8 times, whatever. So the heart of any cosmic imagery is going to be a tracker. This tracker will handle up to maybe a 400 millimeter lens, and maybe a 60 millimeter refractor telescope, which is cheaper than a camera lens, probably less than $1,000 for including the eyepieces you need. Professional equipment is not user-friendly. It's not plug-and-play. It doesn't come with very much instruction, if any at all. This is the stuff the professionals buy, and you're kind of required to know how a camera operates and the telescopes operate and equipment operates. So you have to know things. Which leads me into the next topic. We only have this incredible imagery nowadays because we've digitized everything, but we've married the digital camera with incredible processing power and data storage. We married it with the telescope, and as I've said before, the telescope sees virtually nothing through the eyepiece. But when you just add a few seconds exposure time, you begin to see Hubble-like imagery that will stun you. I know several people that went out and bought a 10-inch reflector and expected to see something beyond the planets. Oh, it'll image the planets really well. And there's a reason for that, but it won't image anything very well. It does, but not like a refractor. A reflector is looking through a mirror, and sometimes, in my case with the RC, it's a mirror, a special type of quartz parabolic mirror that's married with some three sandwiched lenses, ground lenses, and so it is actually a copy of the Hubble, but it's 3 times or more the cost of a normal reflector, and twice the price of a Cassegrain 8-inch. If price means anything. There's a lot of reasons. It's a carbon fiber tube that reduces what's called Well, it seems I've overlooked something quite important in astro imaging of part one. The second part really should be about the moon, because we can still do that with camera lenses and don't need to go to a telescope. And it's a very easy target. It's always there hanging in the sky most of the time. So we need to address the best way to image the moon. Well, the best way to image the moon is to, once again, have a tracker. What the tracker is going to do is it's going to allow us to shoot a video recording up to about 10 minutes, start at 5 minutes, while we're tracking the movement of the moon with our highest powered lens or microscope. We find that when we don't track it, it moves out of frame very, very quickly. So what we do is we shoot this very long tracked image, and then we run it through a free software program called Registrax. And what it's going to do is it's going to take every frame of that 10-minute terabyte worth of information, and it's going to make one image out of it that you get to adjust. And then you can import it over into a couple of programs, either Adobe Photoshop or Raw Lab, or you can take it over to PixInsight even. Actually, I think PixInsight may have a video processing. But anyway, that's how they do it. And these are done with inexpensive little cameras for about $300 called a QHY5 Series 3 Sony will do it for you. That's what I use. It's a tracking cam, so you're going to need it later anyway. But it also does great for the planets. Now you can get a better planetary cam, which will be a better guiding cam later, and they can run over $600, but or more. You can get one of those to shoot through a refractor, or to shoot through a lens, or to shoot through a reflector, or anything. But the idea is you have to shoot a video where you then comprise all those stills into one image, one JPEG, one TIFF, whatever you want. For the best moon shots and planetary shots, you really want to move to a telescopic system. But you can start out using a lens like this, and you can expect to produce some imagery which is very similar to this. It isn't bad for a camera lens at 600 millimeter at f10. And this next image is with the Sigma 150 to 600 millimeter lens. But this last picture is something else entirely. This is a little tiny, I think CMOS processing camera, little tiny lens connected to my guide cam and my reflector. Yes, my reflector. No, my refractor. I'm sorry. My 70 millimeter stellar view. And this is a composite of 5 minutes worth of video that I took with SharpCap, another free video in the description box software. And then it was stacked in Registrax. And here you see it, the final result. I imagine about now you're interested in strange. Well, if you're going to image the cosmos and the planets, you are going to get strange. And anybody that tells you they don't have strange, they're lying. But I'm going to leave this up to you to discover on your own. now the famous 2010 South Pole microscope. What is that? Electron microscope. Picture of, I guess, Planet X, calling it Herbacalypse, Hercolibus at the time. I've heard about that. They all seem to fit the same paradigm. I mean, Planet X, discovered by Iris, etc., etc. Now here's my image, which is very odd. This is supposed to be a flare, but flare is overexposed light. It's not supposed to be. It's not supposed to contain data. My image, zoomed out next to Venus. Is that me, or does the light rays look like they're bending towards the flare? Okay. Yeah, I get it. It's a flare. You can explain all the stars in the image, compare it and blink test it to Starry Night, or whatever you got, and then everything but that flare you can account for. Now, you have to realize this was imaged at 30 seconds, open shutter. See, there's data in there. And you know what I get at 600 millimeter? I was using 600 millimeter lens, not one of my telescopes. But when I get data inside a flare that resembles a small dwarf galaxy that I shoot all the time at 30 seconds exposure time, tracked, well, I gotta wonder, because there's no galaxy supposed to be there at that exact time of the shoot on, what was it, Christmas Eve in 2017. And I haven't even gotten to the moon yet. The point is, you get into astrophotography, you're going to image some odd stuff. Be prepared for it and document it, and please share it for the rest of us. This is going to be the end of this broadcast for this time. I haven't covered everything, so I'll pick it up in the next